Okay, here we want to talk about something fun and kind of creative called squeeze theorem. Essentially, it's a tool for what happens if we have a function, we're looking at the limit, and the function maybe does something kind of bizarre, like this one kind of oscillates back and forth a lot as it goes towards zero. In fact, like if I specifically want to zoom in, we can kind of see it just keeps jumping all over the place. And so maybe our methods of like, we can see that it looks like as x gets close to zero, y is getting close to zero, but it might be hard to show a pattern because of that back and forth behavior. And so here's kind of a point traveling along this, like a little roller coaster. So we can kind of see, like even if we looked at the table in our calculator, we'd get this up, down, up, down, up, down. It might be a little harder than normal to really nail down a pattern. And so there's something creative we can do. If we look at what this function looks like, right? It's x squared times sine of 1 over x. Well, one thing that we know about sine is that the highest value, thinking about the unit circle, the biggest value you can get out of sine is 1, and the lowest value you can get out of sine is -1, right? The top and the bottom of the unit circle. And so stepping away from this for 1 second, here's going to be our idea is we're trying to get a limit for something like x approaches 0, and our function was x squared times sine of 1 over x. It was that 1 over that was causing like the jumping back and forth. So things that we know that sine, no matter what it's of, is always in between 1 and -1. So we know the limit of this would always be between 1 and -1. And so what we can do is kind of bound it by a top and bottom function. If this is always between 1 and -1, if I multiply everything by x squared, right, -1 times x squared, this sine times x squared, this is the logic behind this, and 1 times x squared, I know that the function that I care about is always going to fall between -x squared and x squared. So if we go back to our graph and we graph those, what we're essentially coming up with, definitely easier to see once you get to the actual graphing, what we're actually coming up with are upper and lower bounds for this. Let me get my get our writing out of the way. All right, so if we graph y equals x squared, notice how sometimes it's equal to the function at the places where sine of 1 over x equals 1, basically, and sometimes it's less than the function. But see how our function, no matter how much we zoom in, always falls between these two? So now we can use that to our advantage to say, well, if we can figure out the limit of these two simpler functions, right? Maybe this blue one, the squiggly one, the oscillating it's called, was hard to nail down. But if we could take the limit of x squared and -x, which we can clearly see both of those are tending towards 0 at that point, and we know that this one is in between there, right? Sometimes it's, not as tight in between there. This is also why it's called the squeeze theorem. You can kind of watch it. See if I can get it to come from this side. Once it starts heading back, you can even watch the point kind of get squeezed between the two functions. So if I know that this one tends towards 0 and this one tends towards 0, and I know this one is always in between there, then I know that one has to go to 0 because it's got nowhere else to go, right? It gets squeezed in between two simpler functions. So it's kind of fun when you can see it. Zoom in a little. So no matter where, the point gets squeezed in between two simpler functions. And so if we stop and come back to this from our previous logic, we want to know our goal was to figure out this limit. Well, we just showed, make myself a little more room here. We just showed that we know that this limit and this limit and we know that the one we care about is between these. We just showed that this one goes to 0, or literally you can just plug in 0, right? That one's you can do algebraically. It's a pretty simple function. And so that means that the limit we care about, if it has to be greater than or equal to 0 or less than or equal to 0, it has no other option than to be equal to 0. So we squeezed it between these other two to prove that the one we cared about was equal to 0. But I think it's more fun in the animation because you can just literally see the squeeze happening. It gets squeezed between two more simple functions. In other scenarios, if we want to change this a little bit just for fun, like let's say instead of being x squared times sine of x, zoom back out a little bit so we can see our point. Let's say if it was like 3x, notice that one oscillates way more, but then it would fall between 3x and negative 3x, right? Because we know sine is between 1 and negative 1. Fix my window a little bit on this one. And so notice here's our point again, right? Here's our oscillating function, sine of 1 over x. And it always has to stay in between 3x and negative 3x, which are just two lines. So if one of them's always on top, one of them's always on the bottom, we squeeze it in the middle. And I can say if those two simpler functions go towards 0, then I know this whole thing's limit at 0 has to go towards 0. So you're bounding it kind of by that front piece because you know sine can only go between 1 and negative 1.